Welcome back to a new academic year and a new selection of videos from AQA Biology videos by Miss Taylor. We're looking at a required practical today. It is the Osmosis practical, comes from topic B1 and is in paper 1. I've created a grid here that you can see that just helps to not confuse the bits of potato, to enable us to get a good set of results, work with our data effectively, and just make sure that everything runs smoothly. So I've got some cores of potato that look like this, and I've cut these to roughly the same size. They are the same length, same diameter, and I've removed any of the outside of the potato because the water movement through that won't be as effective as if we remove all of the potato skin, that is. And what I'm going to do is I need to get the start mass of each piece of potato, and then I'm going to put them into the test tubes with the corresponding sugar solution. Could be salt solution, we're using sugar solution today. So let's have a look. We've started with our scales on 0. Okay, if they're not on 0, to eliminate 0 error, we just press 0 and get them back to 0. So here's my first piece of potato, and I've got a starting mass of 3.03 grams, and that's going to go into the first tube, and then I'm going to do the same. So again, same sort of size tube. My scales are on 0. Look at that, almost exactly the same. Okay, but never make the assumption they're all going to be the same just because they're cut to the same length. Go again. It's on 0. I can't believe how close these are. This doesn't normally happen, so it is good to always mass your potatoes. Fourth one. Very, very close tolerance today on this. .99, and then the last one, still checking the scales are always set to 0, and we've got 2.99 again. Now we have scales here with high resolution. We're measuring to 2 decimal places. High resolution enables us to get more precise results. Think of precision and exactness as the same thing. If I said to you, how far is it to town? And you said, it's about 2 miles to town. And then I said to someone else, how far is it to town? Well, actually, I can measure on my car. And when I drove to town, I found that it was 2.3 miles to town. That is more precise because there's a higher resolution to it. It's more exact, okay? So we need scales with a high resolution so that we can see these very subtle changes to the mass of each of the potatoes. Now, we've got the potatoes in. We need to work quickly now because we need the pieces of potato to be in the sugar solutions for the same amount of time, okay? And that's going to be at least 10 minutes, if not 20 minutes, okay? And so this one here is 0 molar, so that's no sugar involved, so that's just going to be some distilled water. So I'm just going to put enough in to cover the potato. You could measure the exact volume and have the same volume for each. I don't think it's a necessity. I've got 0.2 molar sugar solution going in this one. And this works really well because I can match up with my placemat here to ensure 0.4 molar, to ensure that I don't get muddled up. And particularly if you've got people working in pairs and they're not communicating as well as they could be, 0.6 molar, it's good to just put everything on a placemat like that. 0.8 molar. And finally 1 molar. Now the whole point of this experiment is to find out the sugar concentration inside the potato. Okay, so some of these, the ones down here, are going to gain mass. Some of them are going to lose mass, and that's because the concentration of the water in this solution is higher in the solution than it is in the potato, because we know there's some sugar in the potato already. So there is a lower concentration of water in the potato, okay, because there is a higher concentration of sugar in the potato. Therefore, water from that liquid is going to move by osmosis into the potato. So the prediction is that this one is definitely going to increase in mass. Water is going to move by osmosis into the potato from the solution, and that's because there's a higher concentration of water in the low concentration sugar solution. So therefore osmosis means the water moves in. There is no movement of sugar, there's only a movement of water. Okay, we should, I would expect, get some increase in the mass of the 0.2 molar, and as we move down we find here that because there's such a high concentration of sugar in the solution, therefore a lower concentration of water, that this potato, the water will move out of the potato by osmosis because there is a higher concentration of water in the potato than in the solution. Now there's two ways we can look at this. We can say a high concentration of water moving to a low concentration of water, okay? Or we can say a low concentration of sugar moving to a high concentration of sugar. I prefer the first one. I prefer to say that osmosis is a movement of water from a high concentration of water to a low concentration of water through a partially permeable membrane. Okay, so we see that there is a high concentration of water in this sugar solution because there's no sugar. Therefore, the water moves into the potato. Over here, the concentration of sugar in the potato is likely to be a lot less than 1 molar. So that therefore, there is a higher concentration of water in the potato than in the solution, so the water will move out of the potato into the solution, therefore becoming lighter. And we should see that it gets lighter just here. Okay, so things that I'm going to do, I'm going to leave that now for about 15 minutes, and then when I come back to you, we'll remass all of the potato chips there. We're going to roll off any excess liquid using a paper towel. That doesn't mean we roll it on the paper towel as much as possible and get all the liquid out. It's just that surface liquid, just to get rid of the excess before we put it on the scales, so that we're not incorporating that in the mass of the potatoes. Okay, so that might be a question that they ask you about removing excess water. They may well ask you a question related to the resolution of the scales in order to gain more precise results. If you imagine if we had scales that were to just the nearest whole number without any decimal points, we'd just be reading these as 3, 3. These would have rounded up to 3 as well. And we might not see those really subtle changes that occur when the water moves by osmosis. Okay, so we'll come back in 15 minutes. Okay, so here we are, we're back again. These potatoes have been sitting in the different sugar solutions for about, well, definitely more than 10 minutes, getting close to 15 minutes. I'm running a bit short on time, so I'm going to go for it now. Hopefully we'll see the mass changes that we hope for. So just to recap, we should see that these potatoes at this end gain some mass, these potatoes at this end lose some mass. They're gaining mass because the water is going into the potatoes from the solution by osmosis, and these are losing mass because water is coming out of the potatoes by osmosis into the solution, because the concentration of water in the potato is higher than in the solution on this end. So let's take our first potato chip, and just to get rid of that excess water, I've just got some paper towels here. I'm just lightly rolling it. I'm not pushing it into the paper, just lightly rolling to take off any of that excess solution. And then I'm going to put it on the scales. And we have got an increase in mass there. So 3.08. Okay. Put that back in there. And then we'll go for the next one. Again, just that light, taking off any excess, not squeezing it out of the potato. Always check those scales are on 0. And this time, oh, we've actually got a slight drop here. That indicates to us currently that the concentration of sugar in the potato is somewhere between these two, because we've got an increase in mass, we've got a decrease in mass. Next one, get rid of any excess, check those scales are set to 0 to remove 0 error. Okay, and we've got 2.99. Oh, there we go, that's that 0 error. Let's get that to 0. .91. Always good just to give it a second to really get the most accurate reading you can. Sometimes it does change just a little bit when it's settled. .83. And the last one, excess liquid removed, 2.79. Now, what I'm going to do next is I'm going to work out the increase in mass. Now, like I said, at the beginning here we've got an increase and then we're getting a decrease. So the decrease are going to have negative numbers. So let's have a look. The increase in mass here is 0.05. So I've taken the end mass minus the start mass. Now, I am never afraid to use a calculator. So if I ever need to just check something, rather than relying on mental maths and getting, you know, a silly mistake, I will always go to a calculator, and I encourage you to do the same, okay? So end mass minus start mass, okay? It's got lighter, so we've definitely got a negative number there, minus 0.02. Again, another negative, it's got lighter. 2.99 minus 3.02 gives us minus 0.03. Okay, now this one, I'm just going to check the calculator, and I don't mind saying that, okay? 2.91 minus 3.04 gives me minus 0.13. Okay, I'm going to do the same again for the next one, because it's always best not to have those errors. Okay, minus 0.16, and there we've got minus 0.20. Okay, so we've done now start mass, end mass, increase in mass. We've used a negative sign to show decrease in mass, and we can see we've got quite a clear pattern. When we come to graph drawing, we're definitely going to get a nice pattern. There doesn't look to be any anomalous results there. Now, because we started out with these starting masses close to each other but not exactly the same, we must do percentage increase in mass, because at the moment these are not completely comparable because they don't have the same starting mass. Converting to a percentage increase will enable us to fairly compare all of our results, okay? Because say, for example, this one started out at 5 grams, okay, it didn't, but let's say it did, we would see a bigger change in the mass because there's more potato, and so that result wouldn't be comparable, okay? So even though they're similar, let's do a percentage change. Now, for that, we are going to do increase in mass divided by the start mass times by 100 to turn it into a percentage. So 0.05 divided by 3.03 equals times by 100 gives us 1. Now it's 1.65. I'm going to say 1.7% increase. Okay, next one. Okay, This one is, it says 0.66, so I'm going to say 0.7, and it's a negative because it's lost mass. Now we have, it says 0.99, so I'm going to call that 1, round it up. Okay, nearly there. Okay, this one, much bigger change. We've got 4.3, and that's a negative again. Okay, we've got 5.4, and that's a negative, and the final one is it's 6.68, so we'll go with 6.7, and that's also a negative. So what we'll look at next is graphing those results to make some conclusions, to work out the concentration of the sugar in the potato. See you soon for that. Okay, let's look at some graph drawing. So I've drawn my axes. They've got percentage change in the mass of the potato on this axis here, and we've got the sugar concentration here. That was our independent variable, and dependent variable always goes on the side axis here. Okay, I'm being careful not to use X and Y, because when we say to people label your axes, they tend to get stuck in that maths format of let's call them X and Y. Okay, so our independent variable goes on this axis here, and our dependent variable goes on here, and ultimately this is what we wanted to find out. We might have actually done the mass of the potatoes, but ultimately we were getting to percentage change in mass. So I've got at 0 moles molar solution, I've got 1.7, so here's 0 and then 1.7. Nice clear crosses when you do this in an exam. They don't like dots, they like clear crosses, and they need to be within 1 square of accuracy. 0.2. Now we've got the minus. We're going below the line now. So 0.2 minus 0.7, which is there. 0.4, we've got minus 1. 0.6, we've got minus 4.3. 0.6 minus 4.3. 0.8, we've got minus 5.4. Okay, and then for 1 molar, we've got minus 6.7. Okay, and now I'm going to do my line of best fit. Now, we've got some slight movement here. This looks like quite a good line, but if we were to follow that line, then it wouldn't go through that sugar concentration axis at all. Remember, the whole point of this experiment is to try and establish what is the sugar concentration in that potato. Now, in some ways, we've got all our data we need in the first 2 points, because we can see that we had an increase and then we had a decrease. However, we need to try and use as much of the data as possible, and we need it to go through as many points as we possibly can. So if we do this with the ruler, and then I've got some points on one side, some points on the other. So if I just put that down on the table and then do my line of best fit, there is a fairly decent line of best fit. So we've established from this that the sugar concentration inside the potato is this point here, where that line intersects the sugar concentration axis there. And if I look at that, I would say that is... Okay, it is 3 little squares in from 0.1. So each little square between 0.1 and 0.2 is worth 0.02. So where that intersects is 0.0, so that would be 0.1, 0.12, 0.14, 0.16. So the intersection there is 0.16 molar solution. Okay, so that's 0.16 moles of sugar concentration inside that potato. That's what we've established from this practical. Hope you found that useful. Thank you.